Okay, we are live, everybody. This is episode number 8 of a physics of Bitcoin. It's February 5th, 2025. Stephen is with me. And, again, for the people that maybe are tuning in for the first time and they are not familiar with the show, it's called The Physics of Bitcoin because we go a little bit deeper in trying to understand Bitcoin. And both of us have a physics background. We are both PhD in physics. In fact, astrophysics, it is specialization within physics. And you may wonder why two astrophysicists are talking about Bitcoin, because we think that actually Bitcoin has a lot of things in common with physical system. It has clear signals, has certain behaviors that can be attributed to causes like network properties of the nature of Bitcoin, and these things actually physicists studied extensively. And also because of a fact that, like many times we have mentioned, Bitcoin, the main core behavior is this power law, and physicists, it's kind of a realm of physicists. Power laws, physicists understand power law better than anybody else because we see them in nature very often, and we use them to make even predictions about the system and also attribute certain characteristic and mechanism to why these power laws are there in the first place. So it's a very appropriate understanding. There are many more things, but physics gives you a framework that many other fields don't have. So we are not saying that necessarily is the only way of understanding Bitcoin, but it's for sure a different angles that many other people don't have. Do you want to add anything else?
Yeah, I do. Bitcoin is highly multidisciplinary. And, after my research career in astrophysics, I went into the supercomputer industry. I went into high performance computing. And so that gives one exposure to, Moore's law and Metcalfe's law and, cryptography and a lot of other things that are relevant. And it takes a very multidisciplinary mindset in order to understand Bitcoin. So, just the physics training helps one to be multidisciplinary. I know you've applied physics in a range of different fields, from gravitational wave astronomy to, monitoring sleep patterns and signal processing. And I think it's the ability to approach problem solving with a broad range of tools rather than relying on a handful of tools.
Correct. So, and today we have an agenda. Like always, we usually, Stephen is actually the agenda guy. I should make my own agenda too. He's much more organized than me. So please show the agenda that we are discussing today.
Okay. Okay. It's February 6th where I am, and also for our Europeans, if they're up early, it's already February 6th. I've got February 5th on as the date here, 2525. So our agenda is to talk about why we understand Bitcoin to have two-phase behavior. And then once you have two dominant phases, you need to treat each phase separately. You should not treat them with identical tools because the phases are very distinct. And so in these first several slides, I want to kind of nail that down. I've shown some of this in the last session, but I have some new slides and some additional analysis here. And then after my portion, Giovanni is going to look at what he's done to take quantile regression and modify it so that you deal with the fact that you're in a bubble phase, really a bubble rise and fall phase where you're highly turbulent relative to the core power law. So I'll talk a bit about the analogy with fluids I'll show a histogram that shows the two phases. And everything I'm showing here is actually Bitcoin versus gold, but the same behavior emerges with Bitcoin versus dollar analysis. And it's just the power law is slightly less steep. It's about 5.5 is the power law index rather than 5.8. I'll show another tool, which is the sort of continuous probability distribution. It's called KDA. It shows two phases. And then I apply a dual Gaussian model. So we can actually fit quite nicely with two Gaussians the logarithms of the residuals that we get after we subtract the power law. And then once I have that, you can assign z-scores or the number of standard deviations, and you do that on a phase-by-phase basis. And then I've even applied the hidden Markov model to try and determine, are we in the bubble rise phase or the fall phase? Is the rise phase ending? And I'll show some kind of preliminary analysis there. I did show this last time, so pardon me to people who've seen this before, but it's good to review. In fluid dynamics, we have laminar flow and we have turbulent flow, and we have a transition zone between those. And in fact, your very heartbeat has both laminar flow and turbulent flow. And so, the fluid can shift back and forth between that. So we have sort of a heartbeat in Bitcoin, but it's a Fourier heartbeat rather than a 1 second heartbeat. So Bitcoin follows the power law trend in this sort of laminar, more stable and ordered. And that's a very strong trend. It's held up over 8 orders of magnitude in price. And then you have these breakouts, and the breakouts tend to be sharp. The breakouts don't always succeed. I've shown these as yellow in this graph. So you have these transition zones. Sometimes it falls back, but when it does fully break out into the bubble phase, it's quite a sharp and short transition. And then price grows actually exponentially and super exponentially above the power law, rising from the bubble and then collapsing in a similar way. Now, this model has no presumptions except for look for 3 phases. Look for a base power law phase, which is the green. Look for a transition zone, and look for a bubble phase.
So, and again, sorry for interrupting, to explain to the audience. In the algo, there is no assumption, right? We subtract the power law, that is the main signal, and then use what are called the residual, that is basically what is left over, right? You subtract price from the main trend, and then you're using this method, and all what this method needs is look for this number of states, right? You don't give any other information. It does.
That's correct. The method called hidden Markov tries to determine which state you're in at any given week. Now, I've normalized the residuals with a 200-week average, but that doesn't make a huge difference actually here. And here we have about 40% of the data points in the baseline, and we have about 20% in the transition, and about 40% in the bubble phase.
Yeah, the normalization is useful because if you don't, the first peak is enormous in comparison with the other, and that confuses, I think, a little bit the data.
Yeah, absolutely. The other thing you notice here is that on the downside, you only go down mostly to -1 sigma or 1.5, but on the upside, you go up to 3 standard deviations. Okay, so this is first applying a quantile regression to the whole data set, and then using the median, which is the 0.5 level, and you extract a 5.5 power law, and then you subtract that, and then you plot a histogram of the remaining residuals, which is the logarithms of how much they deviate from this median power law line. And you see very clearly 2 peaks. One's sharper, the other's broader, but you're in bubble territory once your residuals are above about 0.13. And the median is slightly negative for the main power law core on the left, and it's noticeably positive for the mean of the residuals when you're in bubble territory. And the separation is 0.5 in the log. And that's a factor of 3. So the average price in the bubble territory is 3 times what it is in the core power law region. So having done that, you can also fit something called the probability density technique. Is called KDE. The name doesn't matter, but it's a continuous plot of the probability distribution. So it's a little bit different from a histogram. Again, you see the same 2 peaks, and they're in the same locations with about the same separation and with, corresponding widths. And then again, we have the histogram, but now fit with a bimodal model. So this is 2 Gaussians, one fit to the left peak, one fit to the right peak. And we see the means, minus 0.12 in the residuals and 0.39. So that's a separation of 0.5. And we see the weights. So 55% of the data is in the left peak, their core power law, and 45% of it is in the bubbles, the bubble peak. Okay, so now you can separate those 2. So the left, the green one, is the core power law Gaussian. The right, the red one, is the bubbles, the turbulent region. And again, you see that they have quite different widths and quite different centers. The standard deviation for the core power law is 0.12, and it's more than twice as high in the bubble phase. It's 0.28. So when you observe, when you do an OLS fit, right, or a quantile fit to all of the data, you're seeing primarily the standard deviation imposed by the bubbles, right, not by the core power law.
Right.
Now, that standard deviation in the case of the core power law is a factor of 1.3, and in linear terms, linear price terms. And for the bubble, it's a factor of 1.9. So one standard deviation is almost a factor of 2.
Yeah, let me stop you there, because I need to replicate this result. But if what you're saying is right, it means that 65% of the data is about 30% either way, 32% either way, from some kind of line that is this peak that is, the true power law in a sense. And then the price, it's 30% in both direction. That is crazy, completely crazy.
Right.
That
It's very tight. Yeah.
It's very tight. When people say, "Oh, the power law," do you mean that? This is part of why we're insisting this, because British Odor, for example, is famous to say, "Oh, do you mean that the price can be from this to that?" Because, for example, Fred say these kind of things. It's not true, because we don't mean that during this time when we are not in bubble territory, we could go to the bubble. We don't mean that. We never meant that. And in fact, this analysis shows that in these 2 years, when we are in this first phase, this non-bubble phase, whatever we want to call it, we are within 30%, 65% of the data. In fact, if you want to double, it's 60%, right? So if you go to standard deviation, then it will be, do you remember, it's 95 or 92?
It's 95. It's 95.
95%. So 95% of the data during this time, it's 60% either way. But it seems big, but it's not. In particular, if you're thinking that you can predict these several years ahead, right? You can come up with, you use the theoretical formula, calculate a value, and then say, during that 2 years, we are about 60% either way, and that will contain 95% of the data. And in fact, it's such a narrow power law, power distribution, that actually probably 95, we almost never go to the 95 level. We stay mostly confined to that region. It's remarkable. It's very remarkable.
Yeah, I've got a plot that shows that. If you think, Michael Saylor said 13 million by 2045 is his base case. I said no, 9 million. We differ by about 40%, right? So that says that he's about a little over 1 sigma higher in his base case than the core power law is showing. Extrapolated out, 20 years ahead. Now, it has to prove itself. It has to continue to hold. But, given the history, one has to assume persistence. And then on the side of the bubbles, the turbulence, it's almost a factor of 2. So 68% of the data is between half and 2 times what the mean is, and the mean is 3 times higher than the core power law. That's sort of the thumbnail for it.
Yeah.
Okay. Now, so here we divide the residuals, the green zone, the core zone, and the bubble zone. These are normalized to their own perspective zones. So the numbers are actually much bigger for the high residuals, right? These are the normalized z-scores. So I've helped you by putting the scale on the side. So a z-score of 1 is about 1.3, and 2, it's about 1.7 if you're in the core power law space. And you see the residuals are pretty kind of randomly distributed, all sort of fit between -1 and maybe +1.5.
Right.
And in this case, we're only dividing into 2, not 3 phases. So you're seeing some of the laminar come to play.
I think if you scramble, one of the things I did to show that I scrambled the time, maybe another, in the future we can show a slide of that. It will be interesting to see this where you scramble, because some structure is still there because there are these peaks, but if you scramble the green points where you basically, you randomize the order and then you replot it, it will look pretty Gaussian.
It will look like a Gaussian. It fits the Gaussian very well.
Yeah, exactly.
Yeah, for the high end, the bubble, the residuals, it's a pretty good fit for the Gaussian. It's not perfect, but it's quite acceptable.
Yeah, and that actually is one of the things that some people that know a little bit of math, they criticize the power law because they say, well, if it was a true trend, once you subtract it, you should see Gaussian data. Well, we do for that region, in particular, right? It really looks it. And in fact, if you divide it, that is another reason to divide. You do have 2 Gaussian. That is what I have said from the beginning. There is a signal there. These bubbles that are a different signal from the power law. So you need to separate them and you get to signal. That is something that we do often in physics. And many stat people don't understand it because they don't think in terms of signals.
Right.
It's a completely different mentality about data.
Right. So when you look at the right side and you're looking at the bubble, first of all, the z-score line corresponds to a price that's 3 times higher than in the case of the left side chart, right? And then a z-score of 1 is 1.9 times the base, and z-score of 2 is 3.6 times the base. So it's a much bigger dynamic range, but we've scaled it here. Now, a couple of things you observe. One is that the climb is steeper than the fall in most cases, right?
Yeah, I noticed the same thing. Yeah,
the climb is quite discrete and continuous, and the fall is a little bit messier. And I'm going to show some more support for that. Now, this is back to that other point. This is a quantile regression where I remove the 40, in this case, 44% of the data that was in the bubble phase, and then redid the quantile only for the core power law. And you get this incredible R2 that's over 99.996.
Yeah.
You get a mean power law of 5.58. If you do ordinary least squares, if you do quantile regression, you get 5.57. They're right on top of each other.
Right.
The error in the power law index is only 0.04, less than 1%. And you have a very tight range of slopes for all of these quantile lines. It's only from 5.5 to 5.7, basically. And the R squareds are all 0.9, 0.99.
Mm-hmm.
So, this just shows how tight the relation is if you're only looking at the core power law points. And I know you've done similar things.
Yes. And these shows, in fact, one day what we should do, we should use maybe 10 different regression ways, subtract that data and then try 10 different regressions and show all these regressions show basically the same thing. So don't tell me that a different regression is another. They all show the same thing, at least for the bottom data. They all agree.
Yeah. And OLS is fine. Yeah.
Yeah, it's fine. Actually, you could use OLS.
Yeah.
Typical. There will be no difference.
And you can apply auto regression, but it just doesn't change things much at all.
No.
Yeah.
That confirms, there is a real power law there, a very unique one, because you can go and look at other physics data where people publish paper saying this is a power law, and it's much more messy than this. People will go crazy to have some data. Don't you agree? It's one of the most.
If we have data like this in astrophysics, it's like, oh,
it will go in the textbook. It will go in the textbook. It will be a textbook kind of things.
Yeah. Yeah, imagine you're plotting the main sequence, and you change the mass of the star by 6 orders of magnitude, right? We know it has segments that are power laws, but you have to keep changing the power law, right?
Right.
And you have about 3 segments.
Approximate power laws, and this is like insane. It's like, are we looking at? Is this even real? It's like crazy. People don't realize this. I think we draw a line. Oh yeah, we're drawing a line. No, for 2 professionals in the field to tell you that this is so special and weird, it's something. And I'm sure if there were other 10 astrophysicists, all of them will agree.
Sure. Okay. Now this is just the bubbles, and here I'm applying Markov analysis to try and divide between the rising phases and the falling phases. So the orange dots, it has determined are rising phase, and again of just the bubble region, and the purple dot it has determined is the falling phase. And I've circled the transitions from purple to orange, meaning rising, where it doesn't go back again. So if you start with the 2013 peak and you look at week 100 and something, normalized residual around 1, it starts rising and it never turns back to a purple dot. It just keeps rising all the way up. And I used a 6-week trend. So it's looking at how much the price changed in a 6-week period when it does this hidden Markov analysis to determine the direction.
I imagine that even Markov needs the future data point, right, to come to a conclusion. This cannot be done in real time. For example, we know.
Yeah.
You know what I'm asking? Because it would be cool to have something like this in real time, where every day you kind of identify one of these dots and color code it. But it will need, at most we will know, because usually they're all clustered together, right? We can know what yesterday.
Well, it's not looking at future data. It's only looking at the 6-week trend and past data.
Okay, so in theory, when we could do an update, a daily update of this curve to know where we are.
I actually have an animation of this, so you can look at the animation and watch each dot get added and say, oh, what would I do in that case? What would I do?
Yeah, do you have it now that we can play?
Yeah, I can show it. It's slow, but I can show some of it.
Yeah, that would be so cool.
And then you see on the downside, things are a little messier, but it's still kind of, once it falls, it kind of goes, right?
Yeah.
So where the arrows
even peaks the time when we actually start to go up again, and then it's really so cool.
You see where the arrow is, the transition, back to purple, and then it just falls. So it's really a good exit signal.
Yeah, fantastic.
And I was trying to do something a little bit simpler than a 7-parameter log periodic power law Sornet style analysis here.
Yeah, it's fantastic. It's fantastic.
Yeah. So it worked in 2013. It worked in 2017, both for the entrance
and again,
the
sorry
exit.
to interrupt you one more time, because I'm trying to understand. And the underlying signal, it's a moving average, right? How long of a moving average is?
Well, it's just a 6-week difference. In other words, it's the value of the residual relative to its 6-week prior value. Is that an increase or decrease?
Yeah. And so it's not on a moving window, etc. It's not continuous. It's just these 6 weeks. You found the 6 weeks works best.
Yeah, I tried 4 weeks, and it kind of works like this, but 6-week was a little better.
Perfect. Okay.
Yeah,
I get it.
Okay, and it worked 2017, and it worked on 2021.
Yeah.
Okay, now the next one is the movie. It's 6 weeks, and let's see if this will play. Okay, you can see the dots These are orange dots, so we're rising. This was from the prior peak, so it's going to go purple, and that one ends. That was that 2011 sort of out of sequence one, right? It started 100 weeks, which is 2011.
Yeah.
And so now, you know, we've kind of jumping back and forth a little.
Yeah.
And now we're going up. And there we go. And then you get your exit signal.
Yeah.
It's not perfect, you know, you're off by a lot.
Oh,
but
it's very good.
At least it got you out.
It's a confirmation signal that, yeah, if you put it together with other things, but it will confirm that, yeah, we are in downtrend. It's the bear market started.
And we're going to see an end to this whole bubble phase soon, and it's going to leap over to the next one. So it's got a second. Here, see, it's messier on the downside. You get these dead cat bounces, right?
Right.
And then continued fall. So you don't want to get shaken out.
No.
Faked out by those.
Right. Probably you can assume once you start to see two.
So now we're in the next one. So we skipped over everything. Now we're into the 2013 timeframe.
We are skipping the power law region.
Yeah.
I love it. It's fantastic.
So you have a little bit of whipsaw there, but then it goes.
Yeah, you see, you just found the missing link because I didn't know. Beside, you know, okay, we are in the right time. We are too far away from to the trend, things like that. But this is a completely different, independent, based on dynamic, basically, that method that tells you when we are in a downtrend, when the bear market starts. That is really cool.
Okay, I think we can stop there. We don't need to wait for the next peak, but it looks similar.
We got the idea. Yeah, it's fantastic.
And then I have one more slide, which is this, you know, for people who want to get really into the weeds, there's Sornet's model and his co-researchers. It's this log periodic power law, Didier Sornet out of Switzerland. I know that you've played with this model quite a bit. Right. You know, I've a little bit. It's quite tricky. It's very tricky because it has 7 parameters.
Yeah.
And the equation is shown here. It's basically, well, let me talk about this curve. In the lower right-hand triangle, he's taken 4 bubbles. And this paper is from 2018. So he's taken that 2013 main bubble, but actually 3 segments of it as individual bubbles, and then the big 2017 bubble.
Yeah.
And he's normalized their duration, and he's normalized how much the price rose. Now, he actually used market cap, but so then you've got 4, you know, jaggedy lines in different colors for those 4 bubbles, all normalized. And you can see they kind of fit a commonality of the curve. And he's got 2 curves. The dashed line curve is a simpler version called a hyperbolic version that ignores the oscillations. And the black squiggly line includes the oscillations, which are in that term that's on the right-hand term that has the cosine.
Yeah.
And basically, it's got a critical time and it's got kind of a slope measure. So it's got its own power law inside, but it's not to be confused with what we're talking about when we talk about the.
It's a local power law. It's a local power law.
Yeah.
And
so,
and the beauty is that in this equation, right? Usually you will not have a log there because that represents basically the oscillation that are just linear in a normal sine wave, but these are called log periodic. So if you will take a log of time, it will look like periodic. It will look like the time between the distance between the peak is the same, but because you're taking the log of time. Otherwise, they will look like they are coming closer and closer together. And the oscillation
faster. That's the whole point, is the oscillations get closer and closer together. and you can use this equation to model earthquakes, avalanches,
Yeah.
the propagation of cracks in materials, EEGs in sleep, and oscillations in supernova.
Yeah.
Prior to the
And the
explosion.
entire idea, I read the entire book. If people want, because it's somehow of a popular book, but it goes a little bit deeper. It's called "Why Market Crash." Sornet wrote an entire book about this topic, and this idea is that basically it's some kind of behavior that where people doing herding, they start to behave in a more and more coherent fashion. They became like bosons, right? They start to march together and do things together. They are more and more coherent. And when you have coherent behavior, you see, this is what happened with sleep. The reason why we have huge big waves during sleep, we see these low waves that are very huge amplitude, is because the neurons start to do the same thing together. It's much more coherent behavior. And when you have coherent waves, you start to add the amplitude together. It's a coherent sum of the waves, and that makes the amplitude of the waves big. And this is what exactly you see here. There is this. It's actually another analogy in physics that we can use, right? It becomes a boson gas or something like that, right? There is a much more coherent behavior of the markets, the people. But many people think we have a free will, and maybe we do at the individual level. But when we work as group under certain circumstances, we FOMO together. That is kind of it's intuitive that we do that. And then, but what is not intuitive, a lot of people, that you actually can use physics equation, where people have used it for earthquakes and other things like that, to actually describe human behavior. That is something that many people resist, but it's true. It actually works.
Yeah. Okay. All right. I'm going to turn it over to you.
Yeah. Thank you so much. All right. So I will present now. This was an excellent presentation, by the way. Thank you so much. All right. Okay. So I will start from here, right? So, and I know I made several videos of these, etc. And we don't want to dwell on the polemics. We don't want to bash other people, but at the same time, we want to learn from investigating new things. And so basically, this is a discussion about this approach that is called the Quantile model. And so we will not make it personal at all, but basically the idea, so it's kind of a philosophical approach, in the sense that see, this is one way that you can try to understand what is going on with Bitcoin, right? You can say, hey, look, there are, so actually a couple of things. First of all, there is the underlying signal that is this power law. And then if you are, because there are this deviation, you could say, well, one way of capturing these changes from the bottom is to draw a bunch of other power laws that are all parallel to the main one. So you keep the signal, but now you're looking for deviations that are, in a perpendicular direction to the power law. But another approach could be also, and there are some advantages in doing this, and so disadvantages. One disadvantage is that if these deviations will be all at the same level when we have these bubbles, then it probably will be one of the best way to do it, right? Because now you will have a bottom floor, you will have an upper floor, but we don't have this upper floor, because you can see the peak kind of became smaller and smaller, right, relatively to the floor, right, to the power law floor. So you can, one approach that I followed in the past is to explicitly model the bubbles. Now, in this case, you're not even trying to follow the exact shape of a bubble, because probably it's complicated and there is not like one simple function. Some functions come closer than other. Here I tried sinusoidal waves. I'm not trying to follow the exact shape. I'm trying to kind of almost bookmark where the peak are supposed to be. And the idea is that if these bubbles are periodic, then we can tell where the next bubble is. And I can include a decay because I see this decay. What is surprising is that this decay actually, once you plot it in terms of deviation from the power law, is actually, even that can be described by a formula because it comes very, very close to be basically an exponential. Now, one of the criticism is, but now you're using 3 points that are the peak of the bubbles. But I will show you later that even another approach like the quantile, for example, doesn't solve that problem because you go from fitting 3 points to fitting 3 clusters. It is not much better. It's just a fact that unfortunately we have only 3 bubbles if you include the first one. The reason I don't include it in this oscillation is that it doesn't seem to belong. These oscillations are 4 years apart, while this one is only 2.1 or something like that. So this is why I'm not included. Now, the decaying, that is weird enough, the first bubble also follows this decay, this exponential decay. That is weird. And in fact, Stephen, what is funny, that if you include the first 3 bubbles, and I know it's ridiculous, but it's the R square is something like 0.98, something like that, right? If you connect with the top of the 3 bubbles with a straight line in a log linear chart, it's a straight line. And that straight line has incredible R square. And the P coefficient is actually 0.02. That actually is statistically significant. It is weird that, with 3 points to get statistical significant result. Now, should you take it seriously? Well, it's 3 points. But I have done this analogy. I don't know if you agree with this analogy. Imagine you are a planetary scientist and you discover this very far away planet, maybe by, one of the techniques is the planet moving across the star. It dims the light of a star, and you don't know why this is happening because usually stars don't do that. There are some stars that do that, but not in this fashion. Where it can be explained as a planet moving across a star and making the light dimmer, right? Because you don't see all the light of a star. And this happens in a very periodical fashion. And let's say it happens every 4 years. And so for 12 years, you study this system. And now, because, one passage of a planet will not give you enough information, 2, you're not sure. By the third one, you waited 12 years. Maybe you don't publish a paper that is completely accepted, but it could be an exploratory paper, right? One of these communication or something, whatever technical term is. Will you agree?
Yeah. Well, yeah. For that example, certainly. I mean, you've made a prediction, right? That you've said, okay, I've got a regular pattern. I see the light kind of just drop by some precise amount. I see that again drop by the precise amount, and
right.
it doesn't flare within, right? It's sort of just a drop for a certain duration while it's crossing, and then you see it again.
And you work for 12 years, and one of the reasons you want to do that is because next time it happens, maybe more telescopes will be pointing in that direction. People will prepare for it, and so it's a completely valid thing. What you will do, you will say it's only few data. These are the stats. We are not sure 100%. It doesn't guarantee that happens again. But, let's see what happens. This is what I'm observing. It's a perfectly valid approach. There is nothing wrong because part of doing data analysis is also to reveal to people the limitations of your analysis, and tell explicitly where it can fail. That is completely valid way of doing. There is nothing wrong. So you cannot tell, oh, this is garbage because it's only 3 data points. There are some circumstances like the one I described where it's perfectly fine. And Bitcoin, in a sense, is like that because we don't have a lot of this bubble. We have them happening. If they were happening every year, we will get a lot of data ready. We don't have that. They are happening every 4 years. So it's perfectly fine. Say, look, there is a regularity. We don't know what it means, but there is a likelihood that it happens exactly like it happened before. And if it did, this where it will happen. If you explicitly describe that and you tell people it's not guaranteed, it's just, it seems that this is the pattern, there is absolutely nothing wrong with that. Do you agree, Stephen?
I do. I mean, we have this expectation of a bubble this year, and if it doesn't happen, then we're going to have to rethink.
Right,
because
exactly.
we don't fully understand the causative factors. There's everything from, it may have only to do with people's psychological mindset around the halvings, right?
Right, exactly.
It may have to do with election cycle, but that's just election in one country. The liquidity cycle has a longer period. So
Right.
we don't know the motive driving forces.
Yes.
But we have some sort of quasi-periodicity that for now we assume, and we'll see what happens this year.
So you don't want to throw the signal when you have it. You report it, and then you report the limitations, right, of it. So, but I understand you could say, well, what if I renounce this, or, at least for the moment, I'm trying to not to commit to myself to a periodicity in the signal. Is there another way of describing this bubble where it's more generic, it's more universal? And so there is this method that basically tries to, how it works. It works by organizing the data and sorting it from small values to higher values, and then drawing it using it always uses all the data, but it gives them different weight. There is a formula where it gives more weight to, if you are in the lower quantile, it gives a lower weight, more weight to the lower quantiles and less weight above. So it divides the data in below and above, right? So you choose a certain quantile, let's say 10% quantile, and then you give 90% to the data below and 10% to the data above. And as you go, by the time you're in the middle, you will have 50-50, 50 above and 50 below, right? You will give equal weight to both. Then as you start to go up, you give more and more weight to the data above the quantile than below. This is how it works. And by the time you're at the 95% quantile, you will give 95% to everything that is above and only 5% below. In a certain sense, you are just fitting the top with a little bit of weight of the rest of the data. This is how it works. And I have concerns about this approach. And this is how it looks like. This is a realization of this approach. Okay. And I will tell you what my concerns are, because you will see them better when you go from this drawing, that is the usual drawing that other people that have worked on this model show. They never show this one. And it's exactly the same thing I'm doing now. I'm taking the quantiles and I'm showing these quantiles levels in a log graph. Because in this particular realization, what we are doing, the input is log of time, in particular days from the Genesis block, when Bitcoin was created, and log of price. So this is what you feed to the algo. And then you're asking the algo to use a linear fit. You're going to get power laws. There is no doubt about that. Because that is the definition of a power law. If you're saying find a bunch of straight line in the log space, the result will be a bunch of power law. This is why you see these straight lines. This is what you get with this particular approach of the quantile model. My concern about this is we have this beautiful straight line at the bottom. That is a signal. That is a meaningful physical signal. These other lines are meaningless. They don't have a particular physical meaning. You can draw them. They are fictitious. They are fictional. They don't belong there because there are no power laws at the top. We already demonstrated. You subtract the power law. Stephen did an excellent job to characterize this signal. They look like peaks and decaying peaks. So even if you want to abandon this approach, this idea that we have oscillation, you say it's too specific, I want to describe it in a more general fashion, doing it in this way is not good, because basically you're drawing a bunch of lines, and these lines will have a lot of negative connotations. For example, notice how these lines eventually will meet. What is the meaning of that? See, in physics, we are trained in asking this kind of question. We want to understand what our data are supposed to mean, because usually once we get data, we want to go back to the causes. What is causing this? What is behind this? We want to understand it. Many people don't do that. They are happy to draw a line and give it meaning when it doesn't have any meaning. So it has a problem. Is basically treating as a monolith the entire data set and using the wrong function, the wrong formula to describe this behavior, when we are specifically Stephen show over and over again, that really we are dealing with two types of data. So it's not the right approach. It's okay for the lower part. And now, Stephen has actually a very unbiased method to distinguish where it's good to apply the power law and where it's not. So why don't you do that instead of doing this? And there are other problems, like I say, for example, if you have a signal that looks like this, and when I discuss this with some of the other people that work on this, they didn't like this example because they objected to the fact that the first waves are bigger than some of the other ones. It is not exactly what happened with Bitcoin, but it doesn't matter. You're missing the point, because they can do this too, where you see the peaks are always lower than the next one. So this model doesn't suffer that problem than the other one. But my intention was in all these examples to show that if you have something that oscillates and it decays at the same time, these lines are not good representations of this type of behavior. Why? Because imagine I'm going to assign some particular meaning and significance to the upper quantile, like here, right? You can see it here better. And I'm happy because it looks like, oh, it's doing a great job in following the first few bubbles. Well, notice what happened with the next ones, right? After some time, these bubbles lose connections with that quantile. So that quantile doesn't have any specific significance or meaning.
Highly over optimistic.
Right, exactly.
It's hopium.
It's opium. And you will think that is going to adapt, is not going to adapt. And Stephen, you gave a very good explanation the other time. Why is not going to adapt? You say it's not going to adapt. It's not like as I add more and more bubbles.
Yeah, no, because it's basically anchored by the two ends.
Right.
I don't know what it has to anchor itself to the final point, to the terminal point.
Exactly. It's going to anchor. Basis is going to be anchored. That means it's going to include the highest quantile possible, and also the first one, because this is how it draws the line. So it's going to draw a line that basically, okay, sure, it's some crazy upper limit over there that it gives some boundary, but it's so detached from reality that is useless.
It's going to be wrong until it's right again in 2140 when the last stat is admitted. So
exactly, and that and it doesn't matter if these points are higher, because that you can say, well, but you created a straw man. This is what the other group reply, and it's not, because I create also these where you can see that these peaks are higher and higher. Right? You see here they are higher and higher, and I can create other examples. I can create an infinite number of these examples where it will not work, simply because we are dealing with something that is exponentially decaying, and you are trying to fit with straight line. Straight line will be an approximation of that behavior. We are not really the right behavior.
In physics, we have a number of phenomena that combine both power law behavior and exponential behavior.
Right.
One of those is just thermal black body radiation, right?
Yeah.
Which is power law, below the frequency that's characteristic of the temperature of the body that's emitting the thermal radiation. And then you have an exponential cutoff, as Planck determined. And that's why Planck's constant is named after Max Planck.
Yeah.
And, it's not uncommon to have power laws with exponential cutoffs. Now, what we have is power laws with exponential rises and falls.
Yeah.
And just as in thermal black body radiation, you're going to be grossly wrong if you try to extrapolate the Rayleigh-Jeans power law, beyond the peak. Here, you're going to be wrong if you try to use a power law model when you're in exponential behavior.
Exactly.
What you have is a power law always underneath and exponentials rising and falling on top. So I call it power law plus plus or power law plus minus because you have rise and fall.
Yeah, exactly. So, and it's perfectly fine separating this signal because that is what everybody that deals with signal does in this kind of situation. That is an idea. You want to, you know, a signal is very clear. You subtract that when you look at what is left over, and you're trying to model that until basically you're done, and what is left is just noise. You know, that is entire principle of data analysis. Maybe financial people are not used to thinking that way to the data. I think to me it's so natural to think in that way, and they are not. And Bitcoin looks more like the typical system that physicists deal with than other type of financial systems. So this approach is better in many different ways. And the idea that like this is trying to answer the question of how many points you're actually fitting when you're looking at these quantiles. So by the time I go to the very high quantile, it's the red dots. It's these red dots. You see, it's not really a lot. You're just fitting these. It's not very different from just fitting the tops. Because it's just little clusters. So you go from fitting only the last tops. In fact, you could, even in that case, you could take the last 5 days before the top, 5 days after the top, average that, and then fit that. Does it make it better? It doesn't make it better.
A 99 quantile is 1 week out of every 2 years.
Yeah, and it's separated by 4 years, right? And so it's using the quantile doesn't help you with that. And if you're making all these crazy claims that this upper quantile is supposed to be predictive, etc. For example, in this model, I call it the vanilla quantile. The vanilla quantile gives you $300,000 for the next peak, close to that. If you use some of the highest quantiles, like 99 quantiles, you get close to 300,000. And and if you do it with the decay, that is sure, it's 3 data points, but that decay gives you 200 instead. So we are off by $100,000. And so what is a solution of that? That is a compromise between this idea that you still want to use some kind of statistical method to describe these oscillations. By the way, have you ever seen quantile used in this context? I never saw quantiles almost in all my career. I never saw anybody describing some complicated signal with quantiles. It's not how you do it. But it has some usefulness, and it has like a visual appeal. So you could try to do a compromise. How will you do that compromise? Well, first of all, we say, okay, the quantile method anyway finds these power laws at the bottom. So let's use the quantile method up to a certain quantile. It turns out that 30, 40% percentile is a good boundary. One could use hidden Markov approach and choose, one of the states and basically fit that with power laws, like the regular quantile approach. And then you subtract the rest of the signal from that. Maybe you can use the last quantile that you use, like if your boundary is 30 percentile, use that as your boundary. Then you subtract that trend, and you're left over with this, that are these points here that you're seeing in the screen. And that is very similar to the graph that Stephen showed us. So this is what is left over. And then what you do, if you take the log of this, you will be in a log linear space. And now you can draw lines, because these lines will represent decaying exponentials. Because lines in a log linear space are exponentials. And now you can use a log linear model of linear feet of these log of the deviations, and you should get exponentials. And now you can take these lines. How do you go back to the price? Well, if these lines, in this case, these deviation are supposed to be percentile deviation. So it's a price minus trend divided by the trend. So it's a percent relatively to the trend. So my signal will be simply the price times the trend plus the trend. So I can reconstruct. I can take these quantiles, use this very simple formula, and go back to the price chart. And how this will look like, it will look like this.
Okay.
And you see, now you have a two, and this is why I also draw with different symbols, because you will have it's a work in progress, so I'm not filling the gap for whatever reason, but you can, right? You can arrive until where the gap is. Maybe you can even draw a very thick line to identify the boundary, where the boundary is. And then if you are above, you use these decaying channels. And if you are below, you use just pure power laws. And you draw them with different colors or different symbols to explicitly mention that you are treating the signal with two different approaches. That is completely fine, right? Will you agree that is the logical thing to do in this case?
It seems logical. How different from this is just multiplying by an exponential decay each value that would be the equivalent quantile power law?
Not sure. Explain me.
In other words, you have a power, if you do it the vanilla way, you get a power law for each quantile. Right. Now you could multiply that by an exponential term. There would be a decay term.
But the problem, they are already bent it like this. They are already, see, basically, they are different power laws with different slopes. What is the meaning of these slopes?
Right.
Why they have different slope from the previous one. Now you could draw parallel lines and then make them decay, right? You could do that. You could draw parallel lines all the way up, and then maybe separated by some criteria, whatever it is, standard deviations or whatever. So they have a statistical meaning too, but then make them decay, right? But I think this is a simple recipe. It's simple to code. You can do it, very easily. If you do that through ChatGPT, completely understands what you're describing, and you get a nice result. It even looks good. It looks satisfying that these lines are coming closer and closer together, and they never cross each other, and they never cross the power law. They approximate more and more the power law. Now, those that has a meaning scientifically, we will have to see, because at a certain point, of course, there will be always some room. It's not that we go to zero room from that middle line, but maybe all what we see are these oscillations just within the power law channel. We will never, maybe we don't have bubbles anymore. Maybe that is what happens in the future. Or maybe the bubbles are so small, that are basically it's like a large deviation, that maybe lasts few days or something like that, right? That is actually a prediction. And one of the beautiful things about science is that predictions can be confirmed or not. And, the model then is, something, in science needs to be all the time, you need to have the possibility to invalidate the model, right? Because otherwise it's no science.
I could imagine that the two Gaussians could start to approach each other.
Exactly.
And become more unimodal, but skewed, right? Probably Laplacian, something like that.
So in fact, what you can do, and maybe I can replicate too, why don't you make a movie of that, starting with the first few bubbles, and then add more and more data, and then show if there is happening. Because right now you're averaging 3 bubbles. Well, it will be cool to see how the two Gaussian look like as you add more and more bubbles.
In fact, I did divide the data into 3 sections. I did the first 8 years and the second 8 years. And they were both quite bimodal, and they both had their means about the same place. The means didn't move, but the distributions became narrower.
Okay.
So I've got some data on that. And I did even just the last 5 years.
Yeah.
It did not look too much different from the 8-year. Last 8 years.
So, this is a compromise between this idea of trying to model, each bubble by itself, because it does contain 2 signals instead of 3. It contains the power law signal. It contains the decay. The decay maybe is more universal, because we are still trying to figure out why we have this decay in the first place. And probably has to do with, actually, maybe it's intimately connected with the power law, because it's another form of diminishing returns, and power law have diminishing returns.
It is connected with the power law. I mean, I wrote an article about that already.
Yeah, exactly.
And then, and actually, if you just take pure power law, it would decrease more rapidly than what we observe. So then I said, well, okay, there's a diffusion term that comes out of the bubbles and helps keep it a bit higher. But you would expect that, because basically it should, the root mean squared should be a derivative of the power law, right?
Exactly.
And so just as the power law has declining returns, the RMS, root mean square, which governs the volatility, should also have a power law behavior of a lower order.
Yeah.
And then declining with time.
Right. And, and Plan C, I talked with Plan C recently. He actually is going in that direction to show that it seems that there is some kind of power law behavior of the volatility, etc. It is really cool. And so everything starts to go together. And this is a good compromise because it contains that information about the decay and explicitly model it with the right functional form instead of giving us nonsensical results, that are these intersecting lines, and you're trying to fit lines where way below. And also, it makes a statement that says, look, take very seriously the power law of the bottom, because it's our kind of like backbone of what we are doing, and with a grain of salt, the other ones. Because if you draw a bunch of power laws, you fall in this, uncertainty of which one is the right one. Which one is, you're telling me there is a power law in the data, which one is the right power law? Of course, you say, well, the ones at the bottom, it's the only power law. The other ones are no power laws, are fictional power laws. It doesn't make any sense. And this one, actually, you can see they are really two different forms, and you don't have any doubts. There is a real power law at the bottom, and there are these strange decaying channel at the top. But you should take with a grain of salt. And we will see in the future if actually the bubbles get contained within this, because this is falsifiable. We can check, but it's a good prediction that they are coming closer and closer together, and in this fashion. And for example, one of the tests that we'll see, if we see a bubble at all, because now, if you're looking at the last few months of price action, it seems that we are not going anywhere. But if Bitcoin decides to wake up and have a bubble, the bubble is supposed to be around 200,000. And we will see, there is some predictive value in the next bubble. The next bubble will be one of these events, right? We see often in physics that destroys a lot of models, right? You bring up a little bit more data, and you had like hundreds of models before, and many die, because the new data destroys a lot of models. They are not possible anymore in the light of the new data. That is one of the things that we witness often in physics. And so, it's everything starts to come together, and this is how this looks like in the log linear chart. Again, these channels, they seem to come together and cross, but they don't, because that by design we made it so where they are exponential. So exponential come closer and closer to the asymptote, right? And here we are using the power law as our asymptote, so they will never cross the power law. And so this is basically what I wanted to say today about this. I think it's interesting, right? And it's a good compromise. And I think this is visually appealing. It has all the things that people are looking for, like a bottom channel, a top channel, things in the middle. We can tell where we are in terms of a quantile. And it doesn't commit to a particular period length. That is one of the concerns that some other people have raised. And at the same time, it has the right functional form. It doesn't give you nonsensical answer. And this, supposedly, if this decay is real, is more precise, because you can do it two different ways, by connecting the dots or by using this approach, and you get exactly the same result. You get 200,000 for the next bubble, if a bubble happens in Q4 of this year. This is what and the other one says 300. Like you, Stephen, say, the other method is FOMO. I jokingly compared with S2F. It is an unfair comparison because it's not as stupid and crazy as S2F, but it has some similarity in the sense that you're fitting a power law where a power law doesn't belong. That is kind of one of the scenes of a S2F model. So I'm joking, but at the same time, there is a little bit of similarity in the approach.
If you want to learn when it's time to go above a power law or beyond a power law, you come to the person who discovered the power law nature.
Kind of, right? And I'm happy to have other people thinking in the same way. In particular, given the same training, the same way of thinking about data, that is slightly different. But I think it's correct because we are following a very precise logic. The results are correct in terms of how you can do tests, because that is another thing that many people don't do. I can reproduce. In fact, this is the next thing I will do. I will make a fake model of Bitcoin, because the usefulness of that, you can extend it to the future, right? You can see I'm adding more bubble, how this approach works. Will it follow the bubbles? Will it follow the decay? We can see. I didn't do that yet, but I'm pretty sure, because of how I constructed it, that it will. These lines will continue to follow the bubbles, and will, I call it being connected with the data. They have a meaningful. They are meaningful. These lines, you can say, they are associated with features of a signal, in particular the top, right? If the top line touches all these previous tops, it will continue to do so, while the other ones don't. We just demonstrated that is the case, by my little toy examples. But yeah, this is it. Do you have any comments or questions on this, Stephen?
No, I mean, it's certainly visually appealing. I think you need a name like Crocodile or something for this. But
it looks like some kind of crocodile. The crocodile model of a unicorn model, whatever it is. Anyway, let's go to questions. All right. This is a comment. He's a let me see. You see this? No, you don't see it. I have to scroll up and I don't see. I love Restream, but sometimes it drives me a little bit crazy. Show. Tell me when you see it. Tell me if you see it.
I just saw one comment flash, but
do you see it? Okay, now you see
but it doesn't persist and it goes back. Okay, there it is. Yeah.
Gentlemen, it's a real privilege to learn from you. It's nice to hear some nice comment. Okay, so this is a real question, this one.
Right. So I think, in the past, what I've done is, when I was using just a single fit, and knowing that Gaussian did not fit, that you have a highly skewed distribution, I was still assigning, a z-score based on kind of the single Gaussian statistics, right? How many deviations are you away? And using that to figure, well, how close are we, how far away are we from the base, and how close are we to a top? I think you're better off if you were to use the two modes and first decide, which phase am I in, right? Am I in the core phase? Perhaps I'm in the transition phase, but I'm in the bubble phase. And if I'm in the bubble phase, use the Gaussian appropriate to the bubble phase. Use the distribution and the z-scores for that phase that apply to that phase. And then you'll have a more precise measure of where you fit. And, how far do you want to stretch it? Do you want to stretch it to 1 sigma or 2 sigma? You probably don't want to go much above 1.5, really, because there's a lot of noise as you get further on. This is not in any way suggesting that people should sell their holdings, but maybe just if you decide at some point I need to trim a little bit, or I've got some expenses in my life, you want to take those at an opportune time. And maybe you take some risk off. If you've got some of your portfolios leveraged because it's in master, for example,
right,
you can lower your risk.
Exactly. Or, some people buy futures. This is what I do, right, because I keep my Bitcoin and buy a little bit of, because it's okay. Not that a lot of people are against the idea of trading at all, but, there are so many tools nowadays that allow you to do things like, take a little portion. It's not a financial advice. I'm describing what I'm doing, and take a little bit of my portfolio, put it, I use it as a collateral, and then I buy futures contract. And these, if you study and trying to understand it is part of also learning new skills and understanding how these things work. But there is no, if you do it in a moderate fashion, you're not going against the idea of hodling. Everybody that is a Bitcoin is at least 95% hodler, but it's okay to take 5% and do something more aggressive so you can actually maybe get a little bit more Bitcoins, if you don't treat it as gambling, because the gambling is different than being an investor or maybe even a trader. There is nothing wrong. There is in being a trader. Just learn. If you are interested in that kind of thing. If you are not, don't. But even, for example, another application could be decaying, because, for example, if you can identify where the bottom is, how sellers say sell your shares, etc. That is the time where you probably want to sell your shares. Maybe do something. Maybe be more conservative in your expenses, etc. Because it's a great opportunity to buy. If you are at the top and we have this signal that we are going to go down, maybe you want to wait before buying your next DCA, right? You could put them, you still put aside, because it's a good habit, but put it aside in USDT, for at least a couple of weeks, a month, or whatever. And then when the market cools down and we are, we get a little bit more discounted prices and we are not the top of the FOMO, maybe you can start to do DCA. One could even design maybe a weighted DCA, where you weight the amount of DCA according to where you are in these curves. There are a lot of things. Knowledge, Fermi, it is one of my heroes, the Nobel Prize for Physics, Italian scientist. He had a say that says, knowledge is better than ignorance. I know it sounds trivial, but actually it's great. There is nothing wrong about knowing stuff. Then how do you act on this knowledge is something different. We are trying to give you the knowledge. Then what you want to do with this knowledge is up to you, because nobody can tell you do this and this other. It's a very personal choice. But knowledge is better than ignorance. So it's better to know than not know, okay. Ben Franklin says, this is a room when listen and shut up. You can talk because you can ask questions. So we like to talk with you, if you want to ask questions, etc. That is a way for you to participate. Yeah, exactly. Yeah, it's generally not investor advice. It's more about using physics to understand Bitcoin. Then, knowledge, the beauty of knowledge, that also it has an actionable component, but it's about you do whatever you think is good. Study, understand, and then try things. There is nothing wrong. Don't do stupid things. Don't do degen things. But you can use, in theory, you could use this knowledge, and we give you some examples, but it's up to you. Okay. Yeah, so there is this question that maybe both of us try to understand. I don't know if I understand completely, but basically, maybe it's a question about what makes a new model versus a variation of a model, because that was one of the topic of discussion. My opinion is all these approaches basically reveal the same thing at the bottom. They reveal, in fact, we say one of these episodes, maybe we can go and explain many different regression, right? Like 3 or 4 or 5. Say this regression does this. Regression means we are trying to find a trend, right, through the line, using different type of statistical approaches, and all of them are pros and cons, right? And they are applicable to certain situations. It seems, and if I kind of demonstrated it myself, but we should do a study. Maybe I can do it. You can help me with that, Stephen. Where if you try all these different regressions, they will be all in agreement within few percent. They will all show. That is another way that you could make an argument there is a real signal there. So the quantile, even the vanilla kind of model, the one with all power laws everywhere, it gives you exactly the same result than all the other methods. So up to basically 50% of the data, it's the same model. I don't know why you will insist that it's a different model. It's the same model than the power law. It's a power law. It's just another way of doing the power law. Now, the question is how you represent the top. And let's say there are different approaches, and you can call them technically models. There are different way of modeling the tops. But I don't know. I don't know if you will want to say, for sure, it's not a completely radical way of thinking about Bitcoin. It's simply, okay, I prefer to do it in this way instead of the waves. I prefer to do it in this way with so one thing that you could argue about using a bunch of power laws is I want to do it in a uniform way. I don't want to worry about separating signals, etc. It looks messy to me. It's messy. I don't think it's messy because you have a very precise recipe. It's like saying that, I want to throw all these vegetables and make a soup. Okay, it's another, it's a recipe. You're doing a soup, and then you say, well, I want to layer my food. I want to follow step by step, uh, this recipe because it's not throwing a bunch of stuff all together and you make a soup, right? There are steps to follow in this recipe, right? It's a recipe, and it's a well-designed recipe. So it's not really, for the computer, it doesn't matter. You press a button, you get, nowadays you get, in few seconds, you get the same answer in both cases. It's no more messy than the other. But one deals, in my opinion, more properly with the data. The other one, it doesn't, it's a soup. It gives you a soupy result, and soups are good, but in this case, I don't think so. I think it's a limitation. It basically doesn't do what it's supposed to do, right? It's trying to do something that is trying to describe a top in a way that doesn't have any assumption, but your assumption is that there are a bunch of power laws all over the data. That is the wrong assumption. So you're still making an assumption. So it's not true that you're not making an assumption, and your assumption is wrong because we clearly demonstrated there are no top power laws at the top. Do you agree, Stephen?
I agree.
I'm asking you all the time if you agree because you're silent and I want to understand if you are saying stupid things. So correct me if I say something wrong. Okay. It's great advice. Everybody likes. Yes, if you want to rebalance, right? There is this concept where you want to balance. Some people maybe want to be 50-50 or maybe 70-30, right? Maybe you want to be 70 Bitcoin and 30 cash because maybe if a price corrects itself, you want to buy more Bitcoin when there is a correction. That is another approach that people can have. Or maybe, you want to protect yourself from big, huge crashes, So, this will help you because you can maybe rebalance according to where you are. Maybe you want to be as close as possible to all Bitcoin when you are at the bottom. Maybe you want to be as little as possible. That doesn't mean, get rid of your Bitcoin. It could be you go a little bit lighter, right? So when you are at the top, maybe you go 70-30. When you are at the bottom, maybe 90-10, something like that, right? Why not? It could be a good approach, And the beauty, if you know a little math, or maybe you're a good prompt engineer, you can actually ask GPT to help you and maybe even do back testing of this.
Yeah. There's a question I'd like to respond to. Someone asks, where do you see the final top and what price range can we expect based on the power law?
Okay.
Okay.
Let me
first
find
of all,
what is the question? What the question says?
it's at the bottom of the frame.
Okay.
And now it just moved off the frame, but the one from Drew Yowell.
Drew.
Just go to Drew Yowell next to last in the frame.
Yes. This one?
Yeah, that one. Okay. First of all, there is no final top according to the power law. The price is going to keep rising, right? However, we have a certain amount of wealth in the world, which is about $1 quadrillion, 900 trillion, 1,000 trillion. And all of that sits on a money supply, global M2 money supply for all of the major nations is 100 trillion, just over 100 trillion. So one can imagine that you can carry all the wealth and denominate it with 100 trillion. So if Bitcoin were to get to that level, it would be a $5 million price, right? However, I'm going to get to this cycle issue, but I think it's important to also have this longer term frame. By the time Bitcoin would get to that level, then the money supply would keep rising, right? So you can actually calculate how they might intersect. And by the time you get to the 2040s and possibly in the late 2030s, Bitcoin's value could be equal to the global money supply, which might be 200 trillion or 250 trillion. So then you're already at a $10 million plus price point. For this cycle, if we have the bubble this year, Giovanni talked about it in dollar terms, 200K. Since I showed you some charts that are all based on gold, let me kind of put it into the gold context. Right now, we're below 40 ounces. We're in the sort of 36, 38 ounces territory, and that's close to fair value in the gold regression. In order to break out into bubble territory, we would need to be at 50 ounces for gold. And then it would have to go above that. So it could get to 60, 70 ounces in gold terms, 2 kilogram bars, because those are 32 ounces each. And if the gold price goes up some, say to 3,000, 3,200, multiply that by 60,000, you also get basically a 200,000 kind of number. So, I see it somewhat above 200,000 this cycle, if the bubble develops similarly to the prior two bubbles.
Okay, maybe we take, so one more or two more questions. So there is this one that I think is more for me. Why not to scale the power law through all the data point and use this ratio? The reason why we don't want to do that, I explain. You look at this power law, right? And you recognize a power law. It's a I don't know how to tell you guys, it's not another line. It's something important and fundamental and characteristic of Bitcoin behavior. You give meaning to that power law. And this is where all these scale invariant behaviors, etc., take place. And if you start to draw a bunch of other power laws, which one is the real power law? They have different slope, really different slope, because it's not just, okay, I'm fitting these and, I do it in this way with gold and get this slope because of that. Or these are really different ones because they start to, change the slope significantly.
Can I make a comment on the fundamentals behind this?
Yes, exactly.
The power law is based on Metcalfe's law, and Metcalfe's law is a law that applies to networks. And it says that the scaling goes roughly as the number of users because it becomes more useful for all of the community that have plugged into that network, right? And so, in fact, the adoption of Bitcoin and Metcalfe's law for networks, in this case, a social and monetary network, is the fundamental underpinning. Now, if you go into a bubble phase, then at some point people get priced out. People stop buying Bitcoin because they think it's too expensive. So there's a self-correcting mechanism there on the fundamentals of the adoption. And it's the adoption that underlies the core power law that fits the points that are, at the bottom in the lower 30, 40%.
And in fact, what Stephen is saying, you can see in the data because they did a lot of study. For example, they did a Granger causality studies, both for addresses and hash rate. And you can see when you go in bubble territory, in particular, very, very close to the top, the price drives addresses. And in fact, at a certain point, there is a disconnect. You can see the addresses stop. If you look at how the addresses look as a function of time, you see slightly bending close to where the bubble are supposed, but they don't see these sharp peaks that you see with the price. And what that means, it means that as we come closer and closer to the top, FOMO comes in. The price is disconnected from fundamentals, like, for example, adoption. It's just people pushing the price higher and higher and higher with this kind of herding behavior that we described before, and it doesn't correspond to anything real. While we are saying there are real causes why the prices go up. And there is also the hash rate. The other side is the hash rate. Hash rate, the price, some people say, for example, Max Kaiser is one of these people. They say, because that is what we do here. We try to investigate these things and go to the bottom of it. Some people say, I don't know why. There is a connection. They recognize that connection, but then they say hash rate drives the price. It doesn't. If you do Granger causality test, is a very, very well-known test where you can show what leads what. It maybe causality is a little bit too much because it's possible that there is a third thing that drives both, but you can say which one drives the other. But usually something that comes before the other is the cause. And at least there is maybe a casual chain, and this thing is, before the other one. So it kind of, at least is one of a step of a causal chain. And most of the time with hash rate, price drives hash rate. Is the other way around. There is only in one place where hash rate drives the price. And guess what? What is that place? The bottom. At the bottom, you can show that hash rate drives the price. And again, it's part of our thesis that power law is meaningful. It's not just a line. It reveals some very fundamental properties of Bitcoin. That has both to do with addresses, so adoption, has to do with hash rate. It reveals the network property of Bitcoin. And so you don't want to have a bunch of other power laws that are, first of all, not even the right functional form, that are fictitious, because that kind of, it doesn't diminish the power law because the power law is there, it doesn't matter what you do, but in a sense it does, because you're representing everything with the same functional form when there is not the functional form. And you kind of almost throw away the spatial status of a power law of a bottom that we described you why it's spatial and why it's meaningful. So this approach is a compromise where we say, okay, do you want some nice little lines to represent how the price is decaying, etc.? Let's do it in this way. So there is nothing wrong with this. It kind of merges the two concerns, right? My concern, maybe even Stephen's concern, and concern from people that say, well, let's not fixate ourselves with a particular cyclic behavior. Let's describe it in a more general fashion. This decaying channel approach solves that. It's the middle ground that actually solves all the other problems, So why do it in a different way when this does it better, much better, right? And let's answer these, and maybe, I don't know if we have I think, I think Mike kind of agree. I now understand better his question because he's elaborating further, but let's answer this one. What is the biggest risk power law breaks down? My concern is that not enough capital will flow into Bitcoin to support the power law over time. What do you think? Because he actually did some work on this, Stephen.
Yeah, well, right. I mean, I've looked at Weibel models to try and look at what the terminal total capital would be, because we know that the amount of wealth on Earth is finite, right? And what I found is that you cannot statistically differentiate at this point between those and the power law. What we know is that in order to sustain the power law, more and more capital has to come in. So the fact that we've got new channels opening up, like ETFs, pension funds, potential strategic Bitcoin reserves, sovereign wealth funds, these are bigger channels for capital to flow in. And we actually require those channels in order to sustain a power law and to not have the power law index break down, because indeed, more and more capital has to flow in. Now, the ratio of new capital to new valuation seems to be something like 2.5 to 1. That is, there's leverage there. If you put in, 100 billion of capital, price and market cap go up by 2 or 3 times that on average. And more or less, it's different depending on whether you're in the peaks or the troughs, but it's averaged over the cycle. It's something like that. So the amount that has to go in is actually itself a power law, and it's the differential of the price. So it's a power law of 1 order less. So the amount of capital, if our power law is 5.8 for the price, then the amount of capital that has to go in on an annual basis has to grow as the 4.8 power of the age of Bitcoin. And so you do need these bigger channels and this institutional class and even government class investment to happen. But that does not invalidate the core assumption behind the power law, which is a network, because those are just networks. A pension fund is a network of individuals. A government ultimately is a network of individuals. Now, you have some fat nodes, you have some people that have more power in the decision making, and actually that provides some stability to the network and the power law scale. So it's all consistent, actually, but you do need these larger sluices of liquidity that are bringing that in.
Yeah. And so yes, exactly. So this could be a concern. Like one variation of what you did, Stephen, in terms of your work, will be interesting to see what if that load that now the big companies, right, the large institution need to take, to continue on the power law path, is distributed among individuals, right? Because I'm curious to say how many individuals we will need to do that, and actually, and how much money each individual will have to put, and then maybe the money is so much that it's kind of unlikely that there are all these individuals that will come in, that will do the investment. It will be a way of demonstrating that only large institutions can do this.
Once master goes into the S&P 500, everybody's going to have a piece indirectly.
Sure, indirectly, exactly. But that will be interesting because then we could calculate what will be the average investment, to participate to this, to keep the power law going, and how many people we need. We can do that calculation. That will be maybe something that we can both work on. It will be interesting to do. But yeah, so we need capital. Now, the other way that power law can break, it's up, right? That is actually what a lot of people seem to desire, because the power law, I think, will have many more fans if it was much more aggressive, much more, based on FOMO kind of results or whatever. Many people don't like it because it's conservative, right? And it's kind of a ridiculous conservative, because something that comes up with the power of six.
The 6th power of time is conservative.
Yeah, it's conservative, right? This is how spoiled Bitcoin is. Now, really, I think many people simply are, they are wishful thinking about having missed the boat, right? Because, of course, if you were closer to see, this is how it works. I know that we are going a little bit over time, but and maybe some of the next episode we will talk more about what is this meaning of scale invariance, right? But just to give you a feeling, it works like this, basically. And I'm going to simplify using the power of 6. It's not really the power of 6, but close enough. So it works in this way, right? Every time you double, you take the power of 6. The power of 6 is about 64. What am I doubling? I'm doubling time. So imagine I bought Bitcoin at the start, right? Then I wait 2 years, and then I want to compare waiting up to 2 years versus waiting up to 4, because that will be 2 times the age of a system, right, of Bitcoin. So you are doubling how long you are going to take. You're idling time. You can call it idling time. So you're doubling. The idling time needs to be measured from the start, right? It's not just your idling time. It's how much time is passed since the beginning, since when Bitcoin was created. So imagine you are year 2 versus year 4. So you wait 2 more years and you get 64 more money, right? Your gain is 64 times wherever you started. If you started with under 10,000, you will end up with 640,000, right? In just 2 years. Imagine, right? You put 10,000 and that 10,000 became 640,000. This is what happened to the people that invested in year 2. Starting with, let's say, invested in, yeah, exactly. They waited to time relatively to the birth of Bitcoin. Invested in year 2, you get out in year 4, you get 640,000 if you invested 10,000. Well, if you want to do the same thing now, you have to wait 2 times the length of a system, that is 16 years. You see how it works? This is why you have diminishing returns. You get the same multiplier, you still get 64, but now you have to wait longer because there is a scaling. The scaling is both in the y direction, so the scaling of price, and the scaling of time. So now you can still get 64, but instead of waiting 2 years, now you have to wait 16 years. And in 16 years, you can multiply. But it's still crazy because there are not many investments, in particular with something that, it's at this point is safe as gold or any other commodity. I think it's actually safer than gold. And, at the same time, you can get 64 times your money if you wait relatively short amount of time, it is 16 years. See, this is how these things work. And so, it's pretty amazing. And yes, it can break up in the sense that it starts to do some crazy things. But my answer to that is this. Look at the chart. It tried to do that at least 4 times. Every bubble is a breaking of a power law. And notice what happened. Bitcoin didn't like it. The system didn't like it. It corrected itself. And where did it go? To the power law.
It's like the quark confinement in the proton. The strong nuclear force is a power law plus a restoring spring force.
Mm-hmm.
And the more you stretch the quarks apart, the stronger the gluons pull them back together.
Yeah.
And that's why the 3 quarks can never break out of the proton, unless you're extremely high temperatures.
Yeah.
And it's the same kind of thing. You have this restoring force. And, Sornet models it a little bit differently, which is that the price is exponential and then it gets more steeply exponential. So you call it supra or super exponential. And it gets to a point where it thinks it's going to infinity. And that's, of course, exactly when the avalanche happens.
Exactly.
And it breaks down.
Yeah. So the
And
God
that's the
candle.
restoring force that pulls it right back to the power.
Yeah, we never had God candles in the entire. Stephen said that last time in the entire history of Bitcoin. And in fact, if anything start to look like a God candle, probably want to get out. This is when you want to get out. This is exactly when you are picking up. And this the market corrects and it responds very strongly to that because you got so far away that it needs a correction. And you see it goes all the time. Look how crazy it is. We go back 2 years. We go about roughly 1 year up, 1 year down, and in these 2 years we go back to where we started almost perfectly. You can see the line, right? But this is why we have a support line. So Bitcoin tried so many times to do this, and every time it decided, I need to go back to that support level. I'm trying to personalize Bitcoin like if it was an individual, but it's a living organism. It's the interactions. It represents all the interactions of all the Bitcoiners, all these networks, all these connections. The fact that is for me almost 9 o'clock at night. What is the time in your country, Stephen?
It's noon.
Noon. We are in different continents. You guys are listening to us. That is what networks do. There are all these continuous interactions that you will not see in normal type of investments because Bitcoin is more than an investment. It's much more. And this is why you have all this very interesting regular behavior. They describe that there is something more there acting more. Power laws are related to multiplicative effects. That things multiply because of this nature of connection. I connect with you too. You connect with somebody else, and all this connection creates this underlying mechanism that is shown or identified or revealed by the power law. Is what is going on. So I don't think it will break up. We will see. Again, it's a falsifiable. The beauty of it, it's a falsifiable statement. They think that we are saying it will continue to be a power law. It can be falsified. And this is why it's actually a scientific theory. It's a real scientific theory. They're saying it seems that the power law is the core behavior of Bitcoin. It should continue because of scale invariant principle, but it's a falsifiable statement. So it's a real scientific theory. It's interesting.
Okay. I think that's a good place to wrap.
Yep. Okay, guys. Thank you so much for your attention to follow us. We will see you again next week.